So today's topics are a little bit more conceptual, which I think always goes over a little bit better. My boxes. So we did carbohydrates, and then we're going to do lipids, and we're going to do amino acids, which are a lot more conceptual because they feed into, like, the Krebs cycle is a great, like, it's like this wonder box. It will take fats and break parts of them down. We'll get to that. But then it can take glucose and can take the glucose and move it over to fat, and it can take amino acids and move that into fat. And there's all this interaction, and it all goes around the Krebs cycle. Okay, so today we'll start with lipids, moving on to amino acids, and then hopefully post-absorptive and absorptive states. There is a reason why we store energy as fat. It is very efficient. Fat tissue takes very little energy to maintain, and it's very dense because it doesn't contain, it doesn't have the water that gets stored with it like carbohydrates. Lipids provide a greater energy yield, 9 kilocalories per gram of fat, than glucose or protein, which are both at 4 kilocalories per gram. Fat is the optimal storage tissue. Only triglycerides are routinely oxidized for energy, so they'll be oxidized kind of as your baseline. We like to use them so we can spare glucose. The two building blocks of triglycerides are oxidized separately. If you remember back to 1147, glycerol was a 3-carbon fragment that had hydrogens all over it. I call it the hydrogen umbrella, if you had me. And then attached to each of the 3 carbons is a fatty acid. So when we are going to use fat to generate ATP, we are going to oxidize these separately. So glycerol gets oxidized as a 3-carbon fragment. And then the fatty acids are going to be broken apart into 2-carbon units, because most fatty acids are 14, 16, 18, 20, 22 carbons long. And so those get chunked off into 2-carbon pieces. So we'll start with glycerol. Glycerol should remind you a little bit of something. So glucose was also broken down into a 3-carbon fragment called, anyone remember? So glucose is broken down. When it's broken in two, it is going to form 2 pyruvate or pyruvic acid molecules. You're like, oh, I knew that, right? Okay. So then pyruvate, it then continues through glycolysis and enters the citric acid cycle. So the things to remember is triglyceride is going to be oxidized. Both of the 2 building blocks of triglycerides are oxidized separately. Glycerol is a 3-carbon fragment, and it will pretty much be treated almost like half of a glucose and continue through glycolysis and enter the citric acid cycle. The ATP yield is roughly half that of glucose because glyceraldehyde is only half of a glucose. So the first thing we do with glucose is we phosphorylate it to keep it in the cell. The next thing we do is we break it in half into 2 pyruvates, and then we oxidize each one of those. So the yield is about 15 ATP per glycerol, because the full oxidation of glucose is around 32. It's almost half of a glucose. We missed that first breaking apart where we get some ATP released. Now we're going to go back can show you. Okay. So there's two slides that kind of, I'm going to go back to kind of jog your memory. I can find them. So it's this one. So this is glucose. Okay, so glucose, we bring it into the cell, make it glucose 6-phosphate. Then we phosphorylate it twice to become fructose 1,6-bisphosphate. And that uses up 2 ATP. Okay, so we don't use this stage, but we do use this one where it gets split into the 2 molecules, dihydroxyacetone and glycerol 3-phosphate. Okay, so we had this 6-carbon sugar, we converted it, we broke it apart and made it into 2 3-carbon fragments. Then these 3-carbon fragments are going to get converted to pyruvate, and then they're going to enter the citric acid cycle. So if we go to, do we have glycerol? And it is 3 carbons. It gets converted into glycerol, and my spelling is going to be off, but aldehyde, sorry, 3-phosphate. Okay, so we have glycerol, it gets converted into glyceraldehyde 3-phosphate. This then feeds in at pyruvic acid. Pyruvic acid is going to then feed into the citric acid cycle. So first it has to get decarboxylated. It has to lose the CO2, right? Because it has to get down to a 2-carbon fragment. That 2-carbon fragment combines with acetyl-CoA, well, with CoA, and then to become acetyl-CoA, which then feeds into the citric acid cycle. So glycerol is 3 carbons, gets converted to this glycolysis substrate in glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate gets transformed into pyruvic acid. Pyruvic acid loses a CO2, combines with CoA, becomes acetyl-CoA, moves into the citric acid cycle. And so at this generation, we get 1 ATP. For citric acid cycle, we also get 1 ATP because we have half of a glucose. And then instead of 10 NADHs and 2 FADHs, we're at half of that because we only are talking about half of a, sorry, essentially half of a glucose. It's not 5, it's 1. And then this is going to be about 14. So we get somewhere between 15 or 16. So I'm thinking most of you probably need to review the carbohydrate metabolism one, where we go from glycolysis, we end with pyruvate. But for glycerol, we're going to go from glycerol to glyceraldehyde 3-phosphate and then enter the pyruvic acid and just follow the same chain. But this is a really, like, I would print this out. Like this one here is kind of your key to understanding the reactions, because then you can annotate on it and say, okay, well, glycerol comes in here. Okay, of course, through glycerol, first we have to go through glyceraldehyde 3-phosphate, and then it keeps going, okay? And then you can, maybe write to yourself, we've got 15 ATP. And then we go to fatty acids. So fatty acids undergo a process called beta oxidation. And in beta oxidation, the fatty acid chains, like I said, so fatty acids they can be 16 carbons long, 18 carbons long, 20 carbons long, 22. Almost all of the fatty acids that we ingest are even numbers because they're easier to metabolize. It's just kind of the default mechanism in nature. We can get odd numbered ones, and we do have a separate enzymatic process to convert those. So we can handle odd numbers, but that adds many steps, which we don't want to cover, and it's infrequent. So we had glycerol. Glycerol is a 3-carbon fragment. Glycerol gets made into glyceraldehyde, 3-phosphate, which then becomes pyruvate, which then gets decarboxylated, which means it's going to lose a CO2. It's one of the first steps, so that it becomes acetic acid, plus coenzyme A to become acetyl-CoA, which can then enter Krebs cycle. And you'll get about 15 ATP for each glycerol fragment. So for each triglyceride, we only have one glycerol, so we're going to get about 15 ATP. Okay, now we're going to look at palmitate is going to be our example. The palmitate is a 16-carbon fatty acid. So triglycerides have 3 of these, right? Hanging off. Okay. Palmitate, you lose 2 ATP to activate it. Okay. Not too worried about that. You got to pull it off the glycerol somehow and get it all ready to go through beta oxidation. But then we're going to generate acetyl-CoA. So one of the things I do expect you to be able to tell me is how many acetyl-CoAs are we going to get from palmitate? So acetyl-CoA is a 2-carbon fragment. Palmitate is a 16-carbon fatty acid. How many acetyl-CoA are we going to form? Close. So if you take away the 1, so 8. So it's 16 divided by 2. So we'll form 8 acetyl-CoAs. And maybe you just mistyped it. So we'll have 8 acetyl-CoAs because these are 2 carbons each. So if you start pulling sets of 2 off of this fatty acid, you'll end up with 8 sets of 2. Okay. Then we'll get NADH plus H, so we'll reduce some cofactors, and we'll get FADH2. Okay, now if you go back to that chart that I love, you probably have never, I don't know if you've noticed, but in glycolysis, there are a lot of something produced and a little of the other. So in glycolysis, we get a lot of NADH plus H, which is why the oxidized form NAD plus gets to be a limiting factor, and very little FADH2. So it's a 5-to-1 ratio with glycolysis. But in beta oxidation, you've heard that fats generate a lot more energy. In beta oxidation, every time you rip one apart, like a 2-carbon fragment off, you get an NADH plus H and an FADH2 produced. Okay, so you are going to reduce or will oxidize the NAD plus and get the reduced forms. So the forms with the hydrogen. And this occurs every time we rip off a 2-carbon segment. So we get 7 of these. Okay, because the last time you rip them apart, you get the 2 products. So there's nothing to rip this one off of. So it's 1 less than the number of acetyl-CoAs. So if you have palmitate as a 16-carbon fatty acid example, you would get 8 acetyl-CoA, because each of these is 2 carbons, and 7 NADH plus H's plus 7 FADH2s. If you were given an 18-carbon, let's go with 20. We can go with a 20-carbon fatty acid. You should be able to tell me the number of acetyl-CoAs. 10, very good. And the number of NADHs and number of FADH2s. 9, very good. Okay, so that's one of the mathematical equations that I write it down somehow is if you're given a certain number of carbon fatty acids, you should be able to tell me how many acetyl-CoAs and how many NADHs plus how many FADH2s. Okay. And so that goes to this next one here, where every fatty acid loses 2 ATP to activation. And then acetyl-CoA, from a 16-carbon fatty acid, you get 8 of those. And then it will generate 10 ATP per acetyl-CoA that is formed. And so, and I know this is, don't get caught up in the numbers, okay, because it's different. For the numbers are different from glycolysis, okay? So don't worry. Like I said, don't worry about the working out. We're not going to go through where all of the ATPs come from. 10.5 from FADH2 and then 17.5 from NADH, because this 10 here includes the NADHs and the FADH2s produced in the citric acid cycle. Okay, so you get 1 from substrate level phosphorylation and then 9 from the electron transport chain. I know, lots of numbers. What you do need to know is that it'll generate over 100 ATP. So 16 carbons is 106, and then I'd have to do the math if it's 10, if it's 20 carbons. But for a long chain fatty acid, which is 14 carbons or higher, then it'll be over 100 ATP produced. Okay, and this is the number that's a little bit more complicated because it, like I said, it includes all of the NADs and FADHs that have been produced in the citric acid cycle. So you just have to kind of trust me that for each acetyl-CoA, there will be 10 ATP produced. And then these, the electrons don't lose all of their energy. They have to live a little bit of energy to regain back to water. So these costs have these values have been theoretically derived. Okay. So what you do need to know, right, okay, is that glycerol is broken down to glycerol aldehyde 3-phosphate, which then goes to pyruvate, which then enters the citric acid cycle, and it will generate 15 ATP. The fatty acid component gets broken down into acetyl-CoA, so that 2-carbon fragment. So if it's 20 carbons, you get 10 of them, plus NADHs plus FADH2s at a value of 1 less than the number of acetyl-CoA. Okay. And that they will generate over 100 ATP. And that number varies depending on the length of your fatty acid. Okay, so you don't need to know like this second column. So when glycerol and fatty acids are not needed for energy, they are going to be stored as triglycerides. And that is called lipogenesis. So lipogenesis is triglyceride synthesis that occurs when cellular ATP and glucose levels are high. 50% is stored in adipose tissue, 50% is deposited in other areas, such as intramuscular triglyceride or in the liver. Glucose is easily converted to fat because acetyl-CoA is an intermediate in glucose catabolism and the starting point for fatty acid synthesis. So you can't just eat all the sugar you want and think, I'm not going to store it as fat. Unfortunately, it is easily converted through citric acid cycle intermediates into fatty acids. So we can't get off that easily. So lipogenesis is triglyceride synthesis, and it's going to happen. We're going to revisit this when we get to something called the absorptive state. But basically, we have all the ATP we need. We have a lot of glucose, so we don't need to spare glucose. We have a lot of glycerol around. We have a lot of fatty acids. We're just going to go ahead and store it. So lipolysis is the reverse. So this is the breakdown of stored fats into glycerol and fatty acids. Fatty acids are the preferential fuel of liver, cardiac muscle, and resting skeletal muscle. This is going to be what's called glucose sparing. So the liver is going to store a lot of glucose in the form of glycogen for the body, but it doesn't want to use it all up because its job is to be a glucose bank. So you can't really steal from your own stores, right? So the liver, in order to protect its glucose stores, actually it runs off of a lot of lipid oxidation. Cardiac muscle runs pretty much on fatty acids, and then resting skeletal muscle will as well. Lipolysis is accelerated when carbohydrate intake is inadequate, because this is again going to be glucose sparing. It'll say, let's give you guys as many fatty acids as you can use, and then tissues such as the brain, which can only use glucose, or ketone bodies, which we're not going to get into, then it will leave that glucose for the brain. Okay, so you do need to know the definitions of lipogenesis. So lipogenesis is you start with glycerol and fatty acids, and your product is triglyceride. It occurs, so what state does it occur? It's going to occur in something called the absorptive state, where we get high ATP and high glucose levels. Lipolysis, you start with triglyceride and end with glycerol and fatty acids, and it is going to be accelerated or stimulated with low carbohydrate intake, lower glucose levels. You should know that fatty acids are preferred by the liver, heart, and skeletal muscle, whereas glucose is going to be the primary fuel for the brain. This is an okay figure. It just shows, and this actually should also be labeled as lipogenesis, both these purple ones. It just kind of shows how triglycerides, when you break them apart through lipolysis, you get glycerol, which then feeds in here to glyceraldehyde 3-phosphate to pyruvic acid, which will then continue down to acetyl-CoA and into the citric acid cycle. Fatty acids are broken up into 2 carbon fragments that will also feed in at acetyl-CoA into the citric acid cycle. So this is a summary of lipid reactions and uses. So lipids are going to play many roles in structural material, phospholipids. So that's where you get a glycerol and a phosphate group, and then 2 fatty acids. And that phosphate group is water soluble, and then the 2 fatty acid tails obviously are not. But so it makes a good place, a good material to build that lipid bilayer for the plasma membrane. They're also used in myelin. Cholesterol is used, so phospholipids make cell membranes fluid. Cholesterol makes them rigid because they have a branched tail that gets kind of stuck in there. Cholesterol is also the starting point for all steroid hormones. So for testosterone, estrogen, progesterone, they all start at cholesterol. Okay, so we do need, your liver is always making a baseline of cholesterol. So in addition, we're going to talk about the liver much more in greater detail. We'll talk about lipoproteins there. So beta oxidation is converting fatty acids to acetyl-CoA, and then they go into the Krebs cycle, electron transport chain, that chemiosmotic phase, and we get lots of over 100 ATP. Lipolysis, starting with triglyceride, breaking down and resulting in fatty acids and glycerol. Lipogenesis is the reverse. We're going to start off with acetyl-CoA and glyceraldehyde 3-phosphate, but eventually we'll get back to fatty acids and glycerol to make triglyceride. Triglyceride is always cycling in adipose cells. So in adipose cells, we always have lipolysis and lipogenesis going on all the time. It keeps a constant level of fatty acids in the blood. Okay, so that is lipid metabolism. Are there questions about lipid metabolism? You're like, no, I just need to watch a whole lot of videos. Okay, so now we'll move on to protein metabolism. So one of the differences with carbohydrate and fats is it can be stored in those forms. So glucose can be stored as glycogen, fatty acids can be stored as triglyceride. We don't store amino acids as proteins. Okay. So as proteins deteriorate, which they do, we have structural proteins, we have functional proteins, and both categories are being broken down or bonds broken continually, so they have to be replaced. Amino acids are recycled into new proteins, different compounds. Proteins are not stored in the body. Okay, that's a big thing. So there's 2 things that can be stored: carbohydrates and fats. These can be stored, but proteins are not stored. So when dietary proteins are in excess, amino acids are either oxidized for energy or converted to fat for storage. And not surprisingly, that interaction as to, is it going to be oxidized? Is it going to be converted for fat? All revolves around Krebs cycle. Okay. So for amino acid, this is oxidation. The goal is to produce molecules that can be converted for energy in the citric acid cycle. We're going to pretty much stop there. Okay, so we're going to try and use excess amino acids to generate ATP. As I have previously mentioned, this all occurs through intermediates of the citric acid cycle. So the first thing we have to do is make them compatible. So keto acid intermediates of the citric acid cycle are the rearrangement of glutamic acid, glutamate. So that's 6 carbons, we rearrange it, we'll lose a couple carbon dioxides during the process. We'll end up with oxaloacetic acid, which is 4 carbons, and then we get acetyl-CoA coming in at 2. Okay, so we start at 6, and then we're going to rearrange, we're going to go down to 5, we're going to rearrange, we're going to go down to 4, we're going to rearrange, and then we'll pick 2 back up. So that is Krebs cycle, going from 6 to 5 to 4, pick up 2, and keep going. And at each of these steps, for I think it's 8 steps, you'll generate 1 ATP, but 5 NADH and 1 FAD. Okay, so H2, right? So the reduced forms. So and then those go off to electron transport chain and the chemiosmotic process and generate lots of ATP. But none of those intermediates in here, these are all pretty much carbon, hydrogen, and oxygen, okay? So sometimes there's, 6 of them, and sometimes there's 5, and sometimes it's 4, but we're really looking at carbon and hydrogen products. In no place is there nitrogen, okay? So if you want to play in the Krebs cycle, nitrogen could not be present. It's just not one of those intermediates. So the first thing we have to do for an amino acid, because if you remember amino acids, we have the amino group, we have the R group, and then we have the carboxyl group. Okay. Amino acids cannot participate. The amino group cannot participate. So the first thing that has to be done is get rid of that nitrogen group. At the same time, if this R group, then there's a couple of them, methionine and cysteine, I believe, have sulfur in that R group, that also has to be removed. Sulfur is not allowed. Okay, but once we get rid of the nitrogen, so that amine group, and we get rid of the sulfur, then we can convert to pyruvic acid or a keto acid intermediate of the citric acid cycle. So get rid of that amino group. And the main way of getting rid of that the amino group is, we're going to go over here actually. We're going to transfer it to a keto acid. The keto acid gives it to glutamic acid. So glutamic acid is a very important molecule in amino acid breakdown because it is going to be the amino group receptor. Okay, so we use a keto acid, don't worry about that too much, but the amino acid through a keto acid gives its nitrogen group to glutamic acid. So glutamic acid is the amino group acceptor. Then the liver is going to take the amino group from glutamic acid and make urea. And in doing so, it regenerates this ketoglutaric acid, which to accept more nitrogens and deaminate or transaminate more amino acids. Okay, so amino acids through a keto acid are going to give their amino group to glutamic acid. In the liver, the liver is going to take the amino group back from glutamic acid and make urea. So that first step, we need to transaminate. Sometimes it'll be called deaminate. Some can be done directly without a keto acid. We're not going to go there. We just need to lose the amino group. The amino group eventually ends up on glutamic acid. That is going to accept that amino group. Then in the liver, we are going to take the amino group and make urea. Okay, so you can see how urea is basically two of these amino groups added together. We add an oxygen so that it then is going to be excreted in the urine. So amino acids via keto acid donate their amino group to glutamic acid. At the liver, glutamic acid donates the amino group to the formation of urea, which is then excreted in the urine. So we're going to lose these amino groups. It's okay, we can always get more. And then that regenerates the keto, this alpha ketogluteric acid, leaving us with amino acid fragments that have lost their amino group. Okay, so now we have what are called skeletons. So base of the carbon skeleton. So all of the 20 amino acids, they're going to donate through a couple of mechanisms their amino group, so it's called transamination or deamination, to glutamic acid. In the liver, glutamic acid redonates those amino groups to form urea, which is then excreted in urine. Then, depending on what amino acid you start with, it is going to feed into a Krebs cycle intermediate. So you do not need to know which ones feed in at succinyl-CoA or at fumarate or at oxaloacetate. You do need to know that we start off with an amino acid. It is going to lose its amino group to glutamic acid. Then its skeleton feeds into the Krebs cycle. The amino group gets donated to urea formation in the liver. So basic concepts, not where exactly does it fit into. Okay. All right. So that is the end of amino acid catabolism. And then we move on to the second part. So before we move on, are there questions for lipid or protein amino acid breakdown? Not yet. Okay. Time-wise, okay, we got 20 minutes. Okay, so, and this should be 23.7 to 23.9. I didn't catch that earlier. Okay, but we're going to start at 23.7. We'll move on to 23.8 is the liver, and then I don't think we'll get to 23.9. Our body uses nutrient pools. So we have stores of amino acids in limited amounts. So these are not stores of proteins. These are amino acid pools that transfer RNA can come and pick up out of, okay? Carbohydrates and then fats. The pools are interconvertible because pathways are linked by common intermediates. And where are these common intermediates located? There's one place that links everything. What is the name of that place? This connects all of the pathways between carbohydrate, lipid, and proteins. That common pathway is called, we just looked at it.
Krebs cycle.
Yes, very good. So Krebs cycle links all of the pools together. They will, because most of these so if you just sent me a message, I'll get right back. I'll get back to you at the end. Okay. So most of these reactions are reversible. There are a handful that aren't, but for the sake of simplicity, the vast majority of these reactions are reversible. So if we have glucose feeding in, and then we also can have fatty acids feeding in, it means that we can have glucose feeding in and then back out to fatty acids. Gluconeogenesis takes place in the liver, so that's the only one that has the right enzymes for that pathway. So not every cell has all of the enzymes, but there are cells for each interconversion, okay? But all of that gets linked through Krebs cycle. Okay, so the amino acid pool is used to form all proteins, some hormones, because remember we have amino acid based hormones, and then we have steroid based hormones. So the hormones are either made out of amino acids or they're made starting with cholesterol and moving on. Neurotransmitters, most are amino acid based. And then gluconeogenesis, we can form new glucose from amino acids in the liver. Proteins are lost in urine, hair, and skin cells and replaced typically by diet. And in the US, we have no problem with it unless you're a vegetarian, really vegetarian, vegan. You do have to be more careful because of essential and non-essential amino acids. Okay. Carbohydrate and fat pools, as I mentioned, amino acids are not stored as proteins. So we don't store proteins in the body. For excess carbohydrates, these can be stored as glycogen, fat can be stored as triglyceride. And I will, by the way, I will edit this and get it posted probably later on today, and then you can all have that link. So right now, everything is posted except for the first digestive lecture. So I will need to, I'll post that today too. So I've got a lab exam, and then I will edit this, and then we'll post everything up tonight. Okay. All right, okay, so this is just showing again how proteins go to amino acids go to proteins, and then as we're degrading proteins, they get broken down and they feed into the citric acid cycle. And then they can, this is all reversible. So we can go back to triglycerides. This little cycle just means that we can go back wherever direction we want. Okay, so all of these can convert in and out from each other, but that central point is the citric acid cycle. So now we're going to talk about the absorptive state versus the post-absorptive state. The absorptive state is also called the fed state. It lasts for about 4 hours after eating. Some of that is determined by the rate of stomach emptying, which is determined by what you eat and how fluid it is of what you eat. But this is when the absorption of nutrients is occurring, anabolism exceeds catabolism. So we're going to be building things. We'll build new proteins, we'll build triglycerides, we'll build glycogen, and that rate exceeds catabolism. So the breakdown of those and the oxidation of those. Excess nutrients are stored as fats. Carbohydrate, when we have excess carbohydrate, it's going to be converted in the liver to glycogen. We can also replenish intramuscular glycogen stores if need be. It's probably already good, but that would be a time to do that. And then if things are in excess, will form fat. Liver glycogen remains in the liver, but fat joins protein to form very low density lipoproteins. So we'll be talking about lipoproteins in the next section when we get to the liver. Blood-borne glucose enters the cell. Excess is stored as glycogen in muscle or fat in adipose cells. So the absorptive state, anabolism exceeds catabolism, we're going to be storing excess nutrients. So in the absorptive state, triglycerides are, they're broken apart, they're absorbed, they're reassembled into chylomicrons, which then go into those lacteals. These chylomicrons are going to be hydrolyzed by lipoprotein lipase. These are in the capillary endothelium, and then liberating some fatty acids and glycerol for use or storage. Triglycerides are used by adipose tissue, liver, skeletal muscle, and cardiac muscle as the primary energy source. In the absorptive state, most are going to be converted back to triglyceride for storage. Amino acids, some can be used as fuel in the citric acid cycle. Most are going to be taken up and used for protein synthesis. And this is the kind of the summary slide. In the absorptive state, the major fuel use is going to be glucose. There's always going to be a low level, though, of fatty acid oxidation in liver, skeletal muscle, cardiac muscle, and adipose tissue. Okay, but other tissues will be using glucose as fuel because it's available. Amino acids, it's anabolism over catabolism, so we're going to form proteins. Glucose is going to be stored as glycogen, and glycerol and fatty acids will be stored as triglycerides. And like I said, the liver has its own section, so we'll get there to kind of as its own. This is just a slide that says in the GI tract, we absorb glucose, we absorb amino acids, we absorb triglycerides. Glucose is going to be stored as glycogen in muscle. It's going to be stored as glycogen in liver. It'll be converted over here into triglycerides, and then it will be used as fuel. Triglycerides will mainly be stored, and then amino acids can be converted and used for proteins or oxidative intermediates. The hormonal control of the absorptive state. So the absorptive state is under insulin control. Okay, so post-absorptive, the other one where we're fasting-ish, then that's going to have hormones and nervous system. But for the absorptive state, all roads lead through insulin. And that's because insulin, we're pretty familiar with insulin stimulating glucose transport in skeletal muscle and adipose cells. So when glucose goes up, then the beta cells of the pancreas secrete insulin. And insulin is going to cause glucose transporters that are intracellular to move to the plasma membrane. And this occurs in skeletal muscle and adipose. So glucose transport in skeletal muscle and adipose is linked with insulin. This is called GLUT4. It's an insulin-sensitive transport mechanism. The brain and liver contain GLUT1, which is always in the membrane. So there's no taking it from intracellular and putting it on the plasma membrane. Glucose and liver always have glucose transporters in their plasma membrane. So they will always be taking up glucose. The brain, because that's what it uses, and the liver to store it as glycogen. The liver also has glucose sensors that balance glycogenolysis and then forming in glycogenesis. So building glycogen and breaking it down. But back to the absorptive state. So the absorptive state is under insulin's control. It has the effect that we're familiar with of stimulating glucose transport in skeletal muscle and adipose tissue. However, what is less advertised is that insulin stimulates, so it's a receptor mediated process. So insulin binds, and then it causes this whole cascade of intracellular actions. So it's like, you know, if you're really good at bowling and you hit the top pin, that's like hitting the receptor, and then all these other pins fall. These are all these other metabolic actions that occur because of insulin. Insulin is very, very powerful at changing metabolism. So it enhances glucose oxidation, and it stimulates conversion to glycogen and triglycerides. So after we've eaten, we're in the absorptive state. We are going to we're going to want to store things, right? Okay, that's this one. We want to store it. It's protein. Well, I don't want to store protein. We build proteins, we store glycogen, we store triglycerides. And because of insulin, that increases glucose oxidation. It also increases glucose uptake. But if you're going to take up glucose, you should use it as fuel. And all of this is under the control of insulin. This is why diabetes is a really a monster of a disease that people underestimate. Okay, so insulin rules the absorptive state. So this is insulin directs nearly all the events of the absorptive state. Glucose increases, beta cells secrete insulin. Insulin targets almost nearly every cell, not every cell, but most. It's going to increase glucose uptake. It's going to increase glucose oxidation. It will stimulate protein synthesis. There are insulin-like growth factors. Okay, so it affects that. And then it affects the conversion to triglycerides and glycogen. It's really, really powerful. The post-absorptive state is called the fasting state. So this occurs between 2 and 4 hours after. So let's say well-balanced meal, lots of fiber, it's not too fluid. So after 4 hours, then we enter the fasting or the post-absorptive state. And this is, it's defined as catabolism, so breakdown of fat, glycogen, and protein exceeds anabolism. So this is its definition. The goal is to maintain blood glucose between 70 and 110 mg per deciliter by making glucose available by 4 sources, which are on the next slide. And it is going to promote the use of fat for energy, which is called glucose sparing. So the body can adapt to burn more fats and proteins, which enter the citric acid cycle along with glucose breakdown products. Virtually every other organ except for the brain is going to switch to fatty acids as its major energy source. So the preference of fats for energy is glucose sparing for the brain. A lot of this, so we're going to talk about hormonal control, we'll talk about glucagon, but a lot of what happens here is because we don't have insulin. So a lot of the post-absorptive state is regulated by the absence of insulin. Sources of blood glucose are going to be glycogen from the liver or skeletal muscle. So that lysis, if you remember, lysine is breaking down. So we're going to break down glycogen from liver. This is the first reserve use. This is one of the liver's main functions. Although the liver has about 500 functions, it's one of the few things that we can't reproduce synthetically. We can have artificial hearts, we can have dialysis, but we can't replicate a liver. But we'll get on to that in the next section. So this is about a 4-hour reserve if we were to just use glycogen. Okay, we're not, let's say we weren't, which isn't, we're not going to just use glycogen, we use fatty acids too. Before the liver gets completely depleted, glycogenolysis in skeletal muscle is going to kick in also. Lipolysis in adipose tissue and liver is going to be used. So we have glycerol and we have fatty acids. The amount of fat in the body is going to determine how long a person can survive without food, because most individuals have more than adequate fatty acid stores. Protein can be broken down during prolonged fasting. This will then can extend the amount of time that one could fast. Okay, so blood glucose comes from breakdown of glycogen in the liver, breakdown of glycogen in skeletal muscle. Glycerol can be used for gluconeogenesis. So again, we're generating glucose. Fatty acids aren't made, they're not a source of blood glucose, but they will be used for energy. So, and then amino acids can also be converted into glucose. So these are the four sources: glycogen from liver, glycogen from skeletal muscle, glycerol, and then amino acids. So this is the summary of the post-absorptive state. Remember, catabolism is exceeding anabolism. So catabolism is going to be the dominant mechanism or pathway here. So proteins are going to get broken down to amino acids. Glycogen gets broken down into glucose. This is primarily in the liver and skeletal muscle. Triglyceride will get broken down into glycerol, which can be converted into glucose, and then fatty acids, which can be used for fuel. The major fuels are going to be glucose, because we've got some tissues that need to use glucose, like the brain. And then also, all cells need to use some amount of glucose, because this glucose provides the Krebs cycle intermediates. So we can never, in any of our cells, just go to fatty acids. Okay, we're always going to have to, it's called fatty acids burning in a carbohydrate flame. We always have to have some breakdown of glucose to feed these intermediates. But unlike the absorptive state, fatty acids are now going to play a larger role, much larger role in producing ATP. Amino acids can also be reconverted into glucose. So these are the pathways again. Hormonal and nervous control of the post-absorptive state. So as I mentioned, this is going to be much more complicated. It's got three main players. One of the main players is that there is a decrease or pretty low level of insulin, and that is going to decrease insulin-induced activities. So that is going to be the first player in the post-absorptive state. Is just that insulin drops out. So this decrease in insulin has a cascading effect to decrease all of those metabolic processes that it previously stimulated. Then we have glucagon, which you might be familiar with from 1141, which is released in response to low blood glucose that stimulates the pancreatic alpha cells to secrete glucagon. Glucagon increases glycogenolysis and gluconeogenesis and lipolysis. The big one, though, that we are concerned with is glycogenolysis, because if you start breaking down glycogen, you're going to raise that glucose level back to normal. So glucagon is secreted in response to low glucose levels, but it is considered a hyperglycemic hormone because its effect is to raise blood glucose levels. The sympathetic nervous system is our third player. So 1, we have decreasing insulin. 2, we have increasing glucagon. And 3, we have increased sympathetic nervous system activity. So this can be in response to exercise. It can also be in response to anxiety or stress. And that is going to play a role in the post-absorptive state also. So this is glucagon, blood glucose falls. That's the stimulus. And then alpha cells are going to secrete glucagon. Glucagon stimulates the breakdown of glycogen, the formation of new glucose, mainly from amino acid intermediates. And then it will also stimulate lipolysis of adipose tissue to promote fatty acid oxidation. And then you can also use the glycerol to form new glucose. The sympathetic nervous system, adipose tissue is highly innervated by the sympathetic nervous system. It also will activate the release of epinephrine from the adrenal medulla, which will then have additional metabolic effects. And this initiates the fight or flight response to trigger fat mobilization, so an increase in lipolysis at adipose tissue and an increase in glycogenolysis. So the sympathetic nervous system is going to try and flood the blood with whatever fuel is needed by the body to get away from the bear. So it's going to flood glucose and flood fatty acids. And this is used in exercise as well, not just like panic mode, but we need to have a lot of fuel available during exercise. This is a table that summarizes all of this. So insulin is going to be your primary hormone in the absorptive state. Glucagon and epinephrine, which is part of this sympathetic nervous system response, these are going to be absorptive hormone and nervous control. We also end up with other hormones, growth hormone, thyroxine, which is thyroid hormone, cortisol, which is glucocorticoid, and then testosterone. And these have some varying effects. So these are just known as other right now, right? Okay. We're just saying that these aren't it. It's not just insulin, glucagon, epinephrine. There are some other controls as well. We're going to stop there because we are out of time. And we will do 23.8 and 23.9 at our next lecture.